Okay, so let's get started. You can see there. Right, so we are discussing shortest paths. All right. And we want to look at an algorithm based on the complementary slackness conditions and duality theory in general that solves the shortest path problem. Right? So let's start with the same example as last time. I'm going to redraw the same example. I'm going to change the cost of one edge to make the example more interesting, as I realized this afternoon. So here is the graph that we were looking at, with the vertices S and T being these two, and these are the vertices U, V, and W. And the costs are, so this is the cost I've changed. This used to be a cost 6 edge. I've changed it to 4. Okay, and the rest is the same. So it's 4, 4, 5, 2, and 4, 1, 2, 1. All right. And I want to recall the two complementary slackness conditions that we wrote down. So this is for if Q is an ST path and Y bar is a dual feasible solution. Okay. And from now on, I will abbreviate this to DFS, which does not stand for depth first search in this case. All right. And so for a given ST path and a dual feasible solution, the complementary slackness conditions are as follows. The first condition, yeah. Oh, right. I forgot to share the screen. Thanks, Anand. Sorry about that. This hybrid mode is tricky because I forget that there are people looking at this. Okay. Okay, apologies for that. So here is our graph. Here are the costs on the edges. And I'm just writing down the complementary slackness conditions for an ST path and a dual feasible solution, right? So the first condition was that if for a so let's say, so correct me if I mix up the two. So if I remember correctly, the first condition is for a particular ST cut, if the label corresponding to that cut, so in other words, the Y bar F is greater than 0, then our path should use exactly one edge from this cut. Yeah. And the second condition was for each edge of the graph, if the edge belongs to the path Q, then the corresponding constraint should be tight, right? So then the corresponding dual constraint, which basically says that you sum up the labels of all the cuts, that all the ST cuts that contain this particular edge, and the sum of the labels should be exactly equal to the cost of the edge. Right. Okay. So these are our two conditions, and our goal is to find a Q and a Y bar that will satisfy both of these conditions. As I said last time, we are going to start by focusing on condition 2. Okay, so okay, so we will begin by focusing. Yes, zoom in a bit. Okay, so maybe let's see. Let me try this. Control. Maybe I'll just write it a bit bigger. You can move that. Okay, sure. All right. So we'll begin by focusing on. I'll write a bit bigger anyways on condition 2. Okay. Okay. Is it better for you guys? Yeah. Okay. You guys are okay. All right. Okay. So this is our plan. We want to start focusing on condition 2, and we will try to find a dual feasible solution such that if you look at the tight edges, which we defined, and I'll define it again. If you look at the tight edges, they should contain an ST path. Okay. So recall that for if y bar is a dual feasible solution, right, then we define the slack of an edge. If y bar is a dual feasible solution, the slack of any edge E is going to be the cost of the edge minus the sum of all the dual variables that correspond to cuts that contain that edge, right? Okay. And we will say that an edge E is tight with respect to the current dual feasible solution if the slack of the edge is 0. Otherwise, E is not tight. Okay. So our first goal is going to be to find a dual feasible solution so that the tight edges contain an ST path. Okay. That will basically ensure that the second condition is satisfied. So initial goal, to find DFS such that the tight edges contain ST path. I want to mention one assumption that we are making throughout. We are assuming that there is an ST path in the graph, right? That we know we can check by breadth first search or depth first search, right? So we can very well assume that there is an ST path in the graph. Right? So let me call it a safe assumption. There exists an ST path in the graph given to us. Okay. All right. So what is the first dual feasible solution we are starting with? All zeros, right? So let's do it on this graph. So maybe I'll put it in steps. Step 1. So y bar f is equal to 0 for all ST cuts. And what is the value of this solution? What is the value as per the dual LP of this solution? 0, right? The value is basically we are maximizing the sum of the labels, and so it is exactly 0. Right? So the value of this solution is also 0. Oh. This guy disappeared again. Can one of you go and check if he's around? Yeah. Please tell him to stay around. He might be there. Okay, it's okay. Madhav, the prompt is gone. All right. Lots of technical issues. All right. So this is our dual feasible solution and the value is 0. Right? And we want to find another dual feasible solution which will be better than this one. Right? And what is the current tight graph? Let me just put the tight graphs here. So the current tight graph is there are no edges because for every edge the slack is positive. Right? Because for each edge, what is the slack? It is the cost minus the dual variables containing that edge. Right? They are all 0 and all the costs are positive. Right? So the first tight graph is just this tight graph 1. Okay, S U V W and T. All right. So now we want to figure out how to improve this dual feasible solution. Okay, so that's the main question. Is there a systematic way to find a better dual feasible solution? And so what we are going to do is we are going to keep track of a certain set of vertices. We will call it the set R for reasons that will become clear very soon. Okay, so initially our R is going to be simply the set S. Okay, so that is our set R in the first step. All right. So now looking at this set and the cut corresponding to it, can anyone tell me how we could find a better dual feasible solution? So the idea is we want to look at the cut for this, right? So let's see, can I change the color here? Okay, so let's say we are looking at this cut. See here. Sorry. Oh, it is there in the more pen settings. This one. Oh, I see. Oh, color. Good. Thanks. All right. Okay, so we are looking at this cut, and what is your suggestion? Exactly. Minimum slack, right? Exactly. So that's exactly what we are going to do. We are going to look at this cut and all the edges in this cut and look at their slacks, and we will try to increase the y bar for this particular cut as much as we can, which will basically mean choosing the minimum slack. Right? So I'll just write it down in full detail for now. Right? Okay, so let's look at this cut and what are its edges. It has 3 edges: SW, SV, and SQ. And let's look at the slacks of all these edges as per the current dual feasible solution. Right? The slacks are exactly the costs, right? So it's 4 and 4 for these two, and the last one is 2. And that is our minimum slack. So that means that we can increase y bar for this cut to 2 while keeping all the others y bar equal to 0. Right? So in the step 2, we are going to have y bar of this particular cut. So let me just write it down in full detail here. You're going to set it to exactly 2. Right? And rest remains as is. All right. Okay. So let me put down the dual feasible solutions in red color alongside the. So this one is now set to 2. Okay. And now we need to figure out how to increase it further, right? Notice that the new dual solution has value 2. Clearly it has increased, right? So the value now is equal to 2. All right. So let's repeat the same process. That's what an algorithm is, right? So step 3 is we need to do the same process. The problem is we can't use the same R anymore. So what should our R be? Sorry? Include U. Exactly. So to make that slightly more systematic, to fill in the missing words there, we are basically going to look at the graph formed by the tight edges and look at all the vertices reachable from S, which is why I called it R, right? Okay. So the new tight graph, notice that this edge SU has become a tight edge. So let me just not draw the tight graph every single time. So the second tight graph is going to include the edge SU because it is tight as per this dual feasible solution, right? And we are going to look at the cut corresponding to this component which contains the vertex S. All right. So now our cut is SU. Right? And for this cut, we want to now look at all the edges, see their slacks, and improve the dual feasible solution, right? So, all right. So let's just repeat what we are doing. So, all right. So now let's look at. So our R now has been changed to. Maybe I should write this in step 2 actually. So the new R is S comma U, and we are going to look at partial of R, which is going to be the edges you see meeting this red line, SW, SV, UV, and UT. Right? And what are the slacks of these edges? As per the current dual feasible solution, let's look at it. So what is the slack of SW? 2. What about SV? 2. What about UV? 1. And UT, it is 5, right? Exactly. Right. The first 3 edges, sorry, the first 2 edges were contained in the cut partial S, so we reduced 2 from them, and the other 2 were not contained in that cut, which is the only cut which has received a positive dual value at this point. Right. All right, and here the minimum is 1. So we are going to increase the value of this to 1, the value of this cut, right? So y bar corresponding to partial of S and U is going to be set to 1, right? And as per this new dual feasible solution, so right, the new dual feasible solution is exactly what we had before, except for this particular cut, and its value has been assigned as 1. So as per this, what are the tight edges now? Sorry, SU and UV. This edge has become tight. So this is our tight graph 3. Yep. All right. Okay, we don't have much longer. We have another, I guess, 2 steps to go by looking at the number of vertices, right? Okay, great. So already you can see something about the time complexity of this algorithm. Right? The number of times you'll be doing this makes sense that it will be the number of vertices at most. Okay, great. So let's go to step 4. I'm trying to fit everything here on one page. Let's see if I can manage. All right. And how does R change? What is the new R? S, U, and V, right? Looking at all the reachable vertices from the source vertex S. Okay. And let's do the same business again. Let's look at partial of R. And let me draw that cut. So this is the cut SUV. And let us mark down all the edges. So the edges here are SW, VW, VT, and UT. SW, VW, VT, and UT. And let's write down the slacks. All right, so let's look at SW. It has a cost of 4, and we have to subtract both 2 and 1 because it is contained in both the cuts. Right? So the slack is 1. VW is 1. VT is 2. And what about UT? 4. All right. So here the two smallest slacks are both of these, which indicates that we are now going to add 2 edges in our tight graph. All right. And okay, so let's see. So Y bar corresponding to this particular cut, which is S, U, and V, we're going to set this to 1. And the new tight graph is going to contain both of these edges, SW and VW. Yeah. Okay. Great. All right. So we are almost there. Let's finish it off. And what is the new R? It's everyone except T. Great. So the new R is SUVW. And let's do the same process. Step 5. So the partial of R now has 3 edges. Let me mark this cut. So we're looking at SUVW. So that can be drawn like this, right? And let me also put down the number for the previous cut. We gave it a value of 1, the dual variable. And now we are looking at this last cut here. And let's put down its slacks. So the edges are WT, VT, and UT. And what are the slacks? Can someone tell me? WT is 3. No. WT is 4. VT is 1. And UT is 3. Okay. So WT 4, VT 1, and UT 3. All right. So the minimum here is 1. So we set Y bar corresponding to this particular cut. So it's partial of SUVW. I can just write it as partial of T, right? Because it is also the cut corresponding to the complement set. So we are going to set that to 1. And how does the tight set change? Now we have VT, which is a tight edge. Right? Okay, great. So let me just okay, so we have assigned 1 to this last cut. Okay, so I did not write down the value of each dual feasible solution, doesn't matter, but let's write it down for the last one at least. The value of this solution is how much? The current dual feasible solution. 5, right? Yeah. It's the sum of all the labels, the sum of all the dual variables. Sorry, 5. Notice that at each step we increase the value of the dual feasible solution. We started at 0 and we have ended up at 5. And by observation, you can check that this is best, right? Why? Why is this best possible? By observation. This is a small graph. What is the shortest path here? Right. So in this example, you can actually observe that SUVT is the shortest path, and its cost is exactly 5. So this dual feasible solution has to be optimal, right? By weak duality. All right. Okay, so we have got a situation. This is the last tight graph. I forgot to change the numbering of the tight graph, but this is the, let me just call it the last tight graph. Okay, as per the final dual feasible solution that we found. Okay, great. So in our final tight graph, the graph formed by the tight edges, we have a path between S and T. And it kind of makes sense. It will exist. So long as your original graph had an ST path, you are constantly increasing the size of the set R. Eventually, you will include the vertex T in it, right? So long as all your costs are non-negative real numbers and you are following the steps, you will eventually reach a tight graph that contains the vertex T as well, right? That contains S and T in the same component, to be more precise. All right. Great. So we have gotten to our initial goal, right? This has been achieved. We have found a dual feasible solution so that the tight edges contain an ST path. Now, of course, one idea would be to just take any ST path here and conclude that this is an optimal ST path, right? Does that work here in this example? It doesn't. Can someone give me an ST path in this tight graph that is not a shortest ST path? SWVT, exactly. So let me just put it down here. So the question is there an ST path in our tight graph, in our last tight graph, that is not a shortest ST path, right? And yes, it is, for example, I think it's the only one in this example. It is SWVT. What is the cost of this path? 7, right? S to W to V to T, 7. The cost of this path is 7. However, the cost of SUVT, for example, I think that's the only other path. Is that right? Yeah, there are only 2 ST paths in this example, and the other path is SUVT, and its cost is 5. All right. So what is going on here? Why is one of these a shortest path and the other not a shortest path? Anyone? What must be happening? The first condition. One of these 2 paths, in particular the one which is not shortest, probably should not satisfy the first complementary slackness condition, right? Because if it did, it would have to be optimal by complementary slackness theorem, right? So let's just verify that. Let's draw all these cuts in the tight graph as well, just to have a clear understanding of what's going on. So the first cut was this one. The second cut is this one. The third cut is this one. And the fourth cut is this one, right? And you observe, let me just use our 2 different colors here. So let's say green is the good one. So if you look at the SUVT, it meets each of these red lines owing to the nice drawing and planarity and everything. in exactly one edge. Right? You can clearly see that the green path meets each cut in exactly one edge. However, the other path, let's use, I don't know, blue. If you look at the blue path, there is a particular cut here which it meets in three edges. Which is that? SUV, right? Right. So notice that um, yeah. So here we have the red and the blue meeting once, meeting twice, and meeting thrice. Right. So that's precisely the reason for this anomaly. Not really an anomaly, but this issue, if I may say. Right. So note that SWVT meets partial of SUV in three edges, thus violating condition 1. Right? And this is precisely why it is not a shortest path. All right. So this algorithm so far is incomplete. Right? We need to do something. We got a tight graph which contains a shortest ST path. Right? In fact, let me think about it. Every shortest ST path should be contained in this tight graph. I think that follows from complementary slackness as well. So all of the tight graphs in the original graph will be contained, all of the shortest ST paths in the original graph will be contained in the tight graph that you found at the end. The problem is there might also be ST paths in the tight graph that are not shortest ST paths in the original graph. Right? So how do we fix this situation? So I didn't want to present you the final correct algorithm because then you just don't see the reason why every single nut and bolt is as it is, right? So now we want to try to fix this algorithm because it's not yet a correct algorithm. So how do we proceed with that? Any ideas? Right. Can we make it a directed graph? That is actually one way to do it. Yeah, that is actually the way they do it in the text as well. So we could probably just go with that. My understanding is that almost any way you do it, it's essentially, in some sense, having some sense of orientation. So even if you don't make an explicit directed graph, in some sense, putting orientations on the edges is essentially what you have to do here. Okay, so how shall we put, so rather than constructing this tight graph as an undirected graph, maybe we will construct it as a directed graph and try to fix the situation. Right? Okay, so let's do this. Let's go through the steps again, not in full detail, just the main points, and see how we will be putting the directions on these edges so that the directed ST paths will be shortest ST paths. The others would not be. Right? Okay, so that's exactly what we want to do. So maybe, yeah, let me see if I can make some space here. Okay, this is good enough. Okay, maybe let me erase the edges and just put the vertices. Okay, so let's say we have our 5 vertices, S, U, V, W, T. So at each step, when we construct this tight graph, we will actually construct a tight directed graph. So let's call it a tight digraph. Okay. And I'll talk a little bit about directed graphs tomorrow to make it more formal. Today, I just want to get through the steps so that we all have the algorithm done. And then we will focus on formalism behind directed graphs for those who may not have seen it before, and focusing on the correctness, etc. Okay. All right. So in the first step, our tight graph is just empty, right? Because we have the dual feasible solution, which is all zeros. So no edges are tight in this example, at least. Then we add the edge. Then we change. We go to step 2, and we set a particular cut to value 2, right? And now we are going to include one edge in our tight digraph. How should we put the direction on this? Right. Look at the old R and the new R and put the edges going from old R to new R. Exactly. So we will put it from S to U like this. Okay. Then we improved our dual feasible solution further by assigning a certain cut the value 1, which is the cut corresponding to S and U. Right. And which edges became tight in this case? UV. Right. So UV became a tight edge. So how should we direct it now? From U to V. Because we are doing it in the second step, let me just indicate the step by putting 2 arrows like this. Okay. All right. So it's a directed edge, or what we call an arc in directed graphs. All right. I'm just indicate the step number by putting multiple arrows. All right. Okay. Now we increase another cut, which was SUV. We increase its label to 1, or the dual variable to 1. And now what are the new tight edges in our graph? SW and VW, right? So we got SW and VW. And what should the directions of these be? S to W. And what about the other one? V to W or W to V? Right. V to W, like this, right? Okay. W was the new vertex, right? The other vertices were not. That was the only new vertex in our that was on the same component as S, right? All right. So it's going from V to W. And now we go to the last step. And what is it that we are adding? V to T, right? So in the last step, we are adding one tight edge, which will be going from V to T. Right? And now if you observe the directed paths in this graph from S to T, there is exactly one. It is SUVT. The other path, SWVT, is not a directed ST path. The edge VW is in the wrong direction. Right? This is exactly the trick. So every time we create the tight graph, we'll actually construct a tight digraph by giving orientations or directions to the edges. And these directions will ensure that all your directed ST paths will actually meet the cuts in exactly one edge, the cuts which were assigned a positive value, a positive dual value. Right? This is exactly the trick. And we will formalize all of this tomorrow. So this is how we take care of the second condition. So I'll just put a brief note here. Condition 2 is ensured by putting directions on the edges in the tight graph. Well, it should be a directed graph digraph, right? And this is essentially the algorithm. We'll formalize it and write down in pseudocode or whatever tomorrow. But you get the main point. Anyone can write pseudocode, right? This is essentially the essence of the algorithm. Okay, to be continued tomorrow. All right. Any questions or concerns? Right. So even if you're adding multiple edges, right? So you had a previous R and you have a new R. Your edges will still go from the previous R to whatever elements were not in your previous R set. So there won't be any confusion with regards to adding the directions. Yeah. Yes, it is possible, I suppose. You can construct an example where two different edges become tight and maybe they are not adjacent, right? So they comprise a matching. They are non-adjacent edges. So in that case, it would happen. I don't think it happened in this example. In this example, it never happened. Right, exactly. So yeah. We added SW and VW, but yeah, in I suppose you can construct an example quite easily. So maybe try that out. Yeah. Maybe I'll just put it as a do-it-yourself problem. Um, Construct an example where two new vertices become reachable uh, in a certain step of the algorithm. Yeah. If you find such an example, you can also just post it on Piazza for people to look at. I see that not many people are active on Piazza, so feel free to become more active on Piazza. Okay, good. All right. Anything else we should discuss? Any other questions or concerns? No? Okay, so I'm going to stop recording and then we can have a more regular discussion in class. Let's see if anybody is still there in the. Okay, nobody is there in the meeting. Okay.